Second half of the chapter starts off with a section that focuses entirely on the second derivative. So everything in the beginning of the chapter was looking at the first derivative, theorems, characteristics, and now we kind of jump to the next derivative and talk about what it tells us. So it's called concavity in the second derivative. So let's talk concavity. The word concavity actually means like curvature. So we have two different types of concavity of a graph. It's either concave up, and I'm putting the abbreviations in parentheses because those are the abbreviations you'll see me use, you'll see on AP tests. Concave up, CCU, basically looks like a smiley face. So anything that has that upwards curvature we call concave up. And then the concave down, which we abbreviate CCD, looks basically like a frown or a rainbow. It's that downwards curvature. So by definition, a graph will be concave up if its derivative is increasing. So not the original increasing, but the derivative increasing. A graph will be concave down if its derivative is decreasing. Well, if you want to see if the first derivative is increasing or the first derivative is decreasing, you need to look at the second derivative because that will be the rate of the first derivative. So we kind of derive another layer. So that's everything that's written here. To see if I want to see if a derivative is increasing or decreasing, I'm going to use the second derivative to help me figure out this idea of concavity. So here's our test, and it all is focusing on the sign of the second derivative. If our second derivative is bigger than 0, so this is basically just saying we have a positive second derivative, then that tells me that my original function must be concave up, looking like this. If my second derivative is less than 0, meaning negative, then my function must be concave down, or looking like this. Now, if the second derivative is 0, or if the second derivative is undefined, we call that point a possible point of inflection. Kind of like we call first derivative 0 and undefined critical values, and those are the places where potentially we could get extrema. With the second derivative, when it's 0 or undefined, these are places that we could have what's called a possible point of inflection. So a point of inflection, which I will often abbreviate POI, is any point where your function switches concavity. So switches from either concave up to down or vice versa. So you have that change in sign of your second derivative. My concavity intervals and my points of inflection can be found either visually, which we'll talk briefly, or algebraically. Now, the visual ones are kind of tough. I'm not going to ask as many visual questions with these just because it is so subtle to figure out when a function is changing concavity. For example, if you look at the one in the lower left corner, it's pretty easy to tell in the beginning it starts out concave down because you can see that upside down look. And then the second half is concave up. But to actually tell exactly where that point of inflection happens can be tough. It's like halfway through between. There are some different things we can do with the first derivative, so that the visual is definitely more challenging than the increasing and decreasing extrema was with the first derivative. But we do write it as intervals. So we write an interval that is concave up, an interval that is concave down, and our point of inflection are my x values where those switch. And then the second picture is a parabola, and parabolas are the easiest ones to work with because parabolas have a constant concavity. If it's a parabola that's opening upward, like the one you're looking at, it's always concave up, never concave down. If I flip it upside down, then it's the reverse. Parabolas do not have points of inflection. Neither do lines. So if you're looking at things that have points of inflection, your degree has to be higher than 2 if you're looking at a polynomial in order to actually get a change in concavity. So let's look at the algebraic because that's where we want to spend our time. So I put the steps on here so you can kind of take a look at what we're going to be doing. It's going to feel super familiar from what we did previously because you're really repeating a lot of your steps that you did for the first derivative and putting it in the second derivative context. So your first step is to find the second derivative. So I'm just going to work with the one I have on the screen as we go through. So my first derivative is 4x cubed minus 12x squared. And then my second derivative, derive one more time. Be careful with your arithmetic and your algebra. 12x squared minus 24x. So that's step 1, is to get all the way to the second derivative. Step 2 is you want to see what's going to make that 0 or undefined. Undefined is only going to happen if you have a denominator. Most you're going to be just factoring. So I'm going to take out a 12x. I want to factor it as much as I can. And that will get what's called our possible points of inflection. These are the possible places where the concavity can change. So then we're going to set up our intervals just like we did with our first derivative. So we're going to go from negative infinity to 0, from 0 to 2, and from 2 to infinity. But this time I am testing my second derivative. So when I put these test values in, I want to go back to the second derivative that I just found. Just like we did with the first derivative though, we're going to pick a test point, plug it in, and see if it's either positive, meaning concave up, or negative, concave down. So if I put like a -1 in here, I'm going to get a negative times a negative. That is positive, which tells me that it is concave up. You'll notice I'm not just going to put pluses and minuses because the pluses and minuses have a different meaning with the second derivative. If I put a 1 in, I get a positive times a negative. So I have a negative result. So that means it's a concave down interval. And if I put something bigger than 2 in, like 3 or 4, I get all positive, which means it's back to concave up. So we have two places that it switches concavity, at 0 and at 2. Both places were what ends up being a point of inflection. And then finally, my last step is I do want full coordinates, and I can find that by going back to the original function. If I put 0 into the original function, I get 0. If I put 2 into the original function, I get 16 minus 32, so I get negative 16. There are not different types of points of inflection. We don't call it something different. If it goes from concave up to concave down or vice versa, we just call all of them points of inflection. So let me show you another one, another two actually. So two derivatives, 3x squared minus 12 is my first derivative, and then 6x is my second derivative. That will only equal 0 at 0. It will never be undefined, so that's my possible point of inflection. The reason I call it a possible point of inflection is because it doesn't have to change concavity. It often does, but it doesn't have to. It's just like critical values don't have to be extrema. So we're going to look at what happens before and after 0. So prior to 0, if I put a negative number in, I'm going to get a negative second derivative. So it starts off concave down. After 0, I'm going to switch to concave up. So I do indeed have a point of inflection at 0. And if I put 0 back into my original function, I get 0. Last one, I do want to rewrite this. Most of your derivatives are very easy, but if you have something that you need to use, like this one's a chain rule, you want to rewrite it to make it easier on yourself. So my first derivative, power out front, power 1 less. Derivative of what's inside is just 1. And then my second derivative, I'm going to do it again. Power out front is going to give me a positive 30. Power 1 less is going to be negative 4. And again, the derivative of what's inside is 1. So my second derivative ends up being 30 over x plus 1 to the fourth. Well, that will never equal 0 because in order to check and see if a fraction equals 0, you want to look at the numerator, and the numerator doesn't have a variable in it. But it does have a place where it would be undefined, and that happens at -1. So we're going to say we have a possible point of inflection at -1. So I'm going to look at what happens both before and after -1. Looking at my second derivative. If I put -2 in, for example, I end up with a positive on the bottom because I'm taking it to the fourth. If I put +2 in or something positive, I'm still going to get a positive because here's why. This sign is going to guarantee that everything ends up being positive because it's an even power. So I am always positive second derivative, so I'm always concave up. I have no points of inflection. Let's talk about what this one looks like, just to give you an idea. This graph, what's actually happening at -1, it's actually an asymptote. I can't put -1 even into the original function. So it is a vertical asymptote. This one, I call these graphs volcano graphs. I know that's not really mathematically specific, but I have this volcano graph where on each side it's approaching the vertical asymptote, and you'll notice that it is concave up on each side. We call these branches. The technical name for this is an inverse square graph. Again, volcano makes sense to me, and both sides are concave up. So that's the basics of second derivative and concavity, how we find the intervals and how we find the points of inflection.